Hello. Thus far, we have seen the four carboxylic acid derivatives and their structure, and now we're going to talk about their reactivity. On the previous page of this handout, number 11, it says here that the acid chloride is the most reactive. Then follows an anhydride, ester, and amide. And on this page, I'm going to try to attempt to explain two different ways to explain this trend of reactivity. Both ways, well, in general, what we have in your derivatives is a molecule that looks like this. We have an acyl group, and on the right, I'm going to put here Lg, leaving group. And reactivity for the carboxylic acid derivatives really talks about how well a nucleophile can attack and then eventually kick out the leaving group. And so again, we have those four derivatives. We're not going to worry about nitrile. We're only going to worry about these four. And so we're focused on the carbon of we call this the acyl group. And let me write that down as well. This here acyl group. There are many names. We call this a keto group. We can't call it a carbonyl because a carbonyl is specific for aldehydes and ketones. Okay, so we have two ways to explain this trend. The first way, we're going to talk about how big the partial positive is on the carbon of the double bond. So we have a carbon-oxygen double bond, and I want to know how big this partial positive is to attract a nucleophile. The nucleophile could be partial negative or a full negative. So you can see there's a charge attraction between that nucleophile and this carbon. I'm going to put a dot right there. Okay? All right, the first one is the acid chloride, which is the most reactive. I'll draw it here. Okay, again, just so we remember, this is the most reactive. And it's going to have a big partial positive. I'm going to put here at the dot right here. Okay? The reason for that is chlorine is electronegative, and we are pulling, I'm trying to figure out what colors to use. We are pulling electron density away from that carbon. Okay, so again, chlorine is electronegative, and it's a good puller of electron. We call it electron density. Okay, that sets the stage. That's the most reactive. So the next most reactive, the pulling is not as effective, and the next most reactive is the anhydride. Now with an anhydride, there are two spots to attack, but I'll make this symmetrical and we'll only focus on this dude over here on the left. Okay, what happens with oxygen is that there's a resonance, and we have to evaluate whether that resonance is making the partial positive charge bigger or smaller. And so, okay, so the resonance that I'm looking at is this. It's not a major resonance, but it's an important one, and it does exist. And look what happens. Did I want to do it that way? Look what happens. Form a double bond here. O minus. And we have this plus. So what this tells me is that well, the other resonance, we got to draw the other resonance actually. Let's go the other way. So let's bring it back. And this is going to be very telling because now I'm really affecting that dot. The dot right here. Okay, everyone agree that these are the three resonance structures? Okay, so my thinking is this, is that we are pumping in electrons via resonance into this dot here. So because of this resonance, especially right like here, we are pumping in electrons via resonance. Okay, so very subtle, but up here it's more of an electronegative effect, pulling electrons away. Here we're pushing electrons into the carbon via resonance, and that lowers or that decreases the partial positive, thus decreasing the partial positive. So it's less partial positive than the situation we have here. Okay. Let's see what happens with an ester. Ester, we're also going to have resonance because we have that oxygen next door. But now, interesting. Now we're not having resonance on both sides. So the only resonance is going to the left. And so if you think about it, well, let's draw it first. Does this make that carbon more partial positive or less partial positive? Well, let's see. If your only option is to push the electrons to the left, then you're pushing more electrons to the left in this situation than you are in this situation. Okay, so it's really, how do we say this? Here we're pumping electrons to that carbon, 1 out of 3 resonance structures. Over here, it's 1 out of 2. So there's more probability, I like saying that, there's more probability that we're pumping electrons towards this dot because we're only having resonance in that direction. So in this case, because resonance in, we'll say, one direction, we're pushing or pumping, let's use the word pushing more electron density to the dot than in the anhydride case. This is not easy, and as you can tell, it's not easy to explain it. But what we're trying to do is we're trying to see via either in electronegativity or resonance, how are we modulating the partial positive on that dot? Are we making it bigger or smaller than normal? Or in this case, compared to this acid chloride. If you're keeping up, another thing that we could say is that chlorine is electron withdrawing, where these two situations, the oxygen is electron donating via resonance. So I think I'm going to write that actually. So this is this chlorine is electron withdrawing group, and in these cases, the O is electron donating via resonance. And because in the ester case, you're only donating electrons to the dot on the left, you're not donating to the right, then you're pumping in more electrons to the left. So this is the same explanation. This guy here. Copy. Paste. Ah, nice. Okay. We'll see if the part 2 is a little bit easier to understand. But this is, again, trying to predict how big that partial positive is on the carbon of the C double bond oxygen is a little tricky. Last one, right? Amides. So now we have to figure out, this has resonance for sure, but is it more electron donating or less than oxygen? So now we have an atom difference, nitrogen versus oxygen. So comparing these two, they're both pushing to the left, but one is a better lone pair donator than the other. How can I describe this? Give me 1 second. How about this? Nitrogen is less electronegative, so it's not holding on to those lone pairs as hard as an oxygen would. So nitrogen. Do I want to say it that way? Yeah, let's say it that way. Nitrogen is less electronegative than oxygen. So it resonates, or it pushes its lone pair more than an oxygen, or so it shares its lone pair in resonance more than oxygen. By sharing those electrons, you are definitely, again, decreasing the partial positive charge of the dot. Okay. Let me do the color coding as well over here. And here, resonance, you're decreasing partial positive of the dot. Okay. Whew. All right, so that is using electrophilicity to describe the reactivity. Again, this is the most reactive, and this amide is the least reactive. Another way you could say least reactive is what? Most stable. Okay, let us take a look at the leaving group. And so the leaving group is this. When we take a look at each of these derivatives, we're going to draw a red dotted line to visualize the leaving group. Now, in the mechanism, it may not leave as how it's drawn. You know, like with acetal formation, to make OH leave, we make it look like water, right? And so some of these you're going to have to protonate to make it leave, but that's not the main point. The main point is, let's just evaluate what the leaving group looks like from the initial structure. Okay, and let me double check my notes real quick. Is there anything else I want to say about this? Give me 1 second. Yeah, I do want to say one more thing. So, as you get less electrophilic, right, this is the least electrophilic. Right, we're going to practice using our correct terminology, and it is less attractive, right, to a nucleophile. To NU. Okay, now I'm ready to move on. The leaving group. Okay, so here we're going to talk about leaving group. the more stable the leaving group, the more reactive, right? Because you want to get to the other side, to get to the right side of the reaction. And so, for instance, if I have the acid chloride, and my leaving group is, my leaving group is the Cl, like this. Again, I'm not drawing the mechanism, I'm just drawing a visual of what does it look like when the leaving group leaves. And so when the leaving group leaves, we kick out a Cl minus, essentially. Right now, you're going to take this on faith if you don't know this already. But this is out of the 4, this is the most stable leaving group of the 4 derivatives. Okay. Chlorine actually is on the second row. It goes like this. The first atom that has a p orbital is boron, then carbon, then nitrogen, then oxygen, right? Valence of what? 4, 5, 6, 7 is fluorine. But underneath fluorine is chlorine. So chlorine is in the second row. So it is much larger than atoms that are in the first row. And large atoms accommodate negative charge better. It's more spread out. Okay, so let's keep that in mind. Next, the anhydride. The anhydride looks like this. We're going to focus on attacking the carbon on the left. And so what that means is this is the cut. And the leaving group in this case looks like a carboxylate. Okay. So here we have our negative charge on an oxygen. Yes, oxygen is more electronegative, but the size of chlorine is more important, and chlorine is much more bigger than oxygen. So this is a less stable anion. So the O minus is a less, let me use a different color. The O minus is a less, it's still stable, but it's less stable than Cl minus. Less stable anion. And it's only because of size. Because we are comparing atoms in 2 different rows of the periodic table. We use size when we compare atoms in different rows. We use electronegativity when we compare atoms within the same row but in different columns. Okay. It's still pretty stable because there's resonance. And that explains why this ester, okay, I need to rush a little bit. This ester has what kind of leaving group? It's an alkoxide. My colors. Come on. Okay. O minus. So this is an alkoxide, as you know. And it's even less stable because there is no resonance. See, this carboxylate has resonance. So this alkoxide, the last one, no resonance. Unlike, right, the carboxylate. Okay? Last and not, least, for sure, because the amides, now we're comparing atoms that are in the same row. And what do we say there? You use electronegativity. So in this case, a negative charge on N is worse than a negative charge on O. worse than on O because O is more electronegative. Oh my goodness. Okay. Sloppy. Okay. Please. It's not going to stick unless you maybe recopy this, maybe word it a little bit differently. Definitely make it neater. Make sure your colors make sense. But again, what we're doing in this last bit is we're comparing the leaving group. The more stable the leaving group, the more reactive the derivative. And that would be the last thing I'll say. More stable the leaving group, the more reactive the derivative. Because you want to get to the other side. You want to have the reaction move forward. So if this is very stable, this will happen very quickly. This is a lot more attractive to the nucleophile and a lot more reactive. Here we don't like this leaving group, so it'd rather just stay stable and not be very reactive and not kick out this leaving group, this N-.